My name is Josh Gargan, and this is my presentation on motion of a falling object. For my experiment, I took a small ball and dropped it from a height of about 1.368 meters. The ball dropped with an initial velocity of 0 meters per second in the negative y direction and fell to the ground. For the purposes of this experiment, we will be dealing solely with the time when the ball immediately leaves my hand to the moment it is about to hit the ground. As you can see from the video, the ball I used is small, and therefore will fall quote-unquote slowly, meaning tracking the ball's position will be a little easier in Tracker. The ball also maintains a relatively straight path along the negative y-axis, and doesn't deviate significantly in the other two cardinal directions. This is ideal as we will be looking at motion along a single axis. As you can see from this image, I uploaded the video into Tracker and extracted the position data from the experiment. I used my height as a reference, and the direction of motion is denoted as the negative y-axis, starting from the point where the ball was dropped. The motion we are analyzing can be explained with Newton's second law of motion, the gravitational force, and the drag force. The second law states that an object will accelerate or decelerate as a force is applied to it. This is explained as the ball is experiencing a net force in the negative y direction, causing the ball to fall towards the ground. By using Newton's equation of motion, we can derive the formula for predicting velocity. We can also manipulate the equation for average velocity to get a formula that predicts position. For these equations, we can approximate that the average velocity equals the final velocity, and our results will be accurate as long as delta t remains small. Newton's law of universal gravitation shows that when an object is dropped close to the surface of Earth, the magnitude of the gravitational force exerted on the object is mg, where g is 9.8 meters per second squared. The second force acting on the ball is the drag force, which is the force experienced on an object as it moves through a medium, opposing the direction of motion. For my code, I inputted the ball's mass and initial position and initial velocity. Delta t was made based off the rate at which the frames were captured from my phone. As the code loops through, the force of gravity and drag are calculated with the equations mentioned. The constant b is calculated by setting the initial y position to be 1.368 meters, the height the ball fell, and plugging in values of b until the final y position is approximately 0 meters. The ball's velocity and position are updated with the two equations mentioned before. This next slide then shows the results of the simulation, showing how the ball falls in the negative y direction. You can already see a difference in the velocity and positions of the ball when drag isn't accounted for. As seen by the graph, the gravity-only curve deviates as time increases and the final y position is overestimated. This is due to the fact that this curve is only affected by gravity, a force that remains constant as long as the mass remains constant. As you iterate through the simulation, the velocity will increase in the negative y direction at a constant rate, and the position will increase in the negative y direction at an exponential rate. The drag force modeled shows a parabolic relationship between it and the velocity, so as the velocity increases, so will the drag force. Because drag opposes motion, this will decrease the net force and eventually balance it out, as seen by the red curve versus the blue curve. The discrepancy between these two curves is most likely due to the fact that we used a drag force based on the proportionality of it with velocity. The actual equation, as shown, is based upon multiple variables, which would account for the gap in the curves. Now, what would be the terminal velocity of the ball, and is it represented by the simulations? Terminal velocity is the velocity an object would reach when the force of gravity balances out the force of drag. In other words, the object would be experiencing a net force of 0 newtons and moving at a constant velocity. This idea can be seen in the graph shown previously for the case with gravity and drag, as the velocity can be seen to level out to a constant velocity of about 0, negative 2.5, 0 meters per second, roughly the velocity the ball in the observed experiment would have reached before it hit the ground. What if there was an initial velocity on the ball rather than starting from rest? Nothing actually would change for the terminal velocity, as seen by the two graphs shown. This is due to the fact that the drag force opposes motion, with a force proportional to the velocity squared of the object, meaning the net force will increase and decrease over time until the terminal velocity is reached that balances out the two forces. Thanks for watching.